So once again, good evening to everyone. And as usual, my name is Ikeshuku and I'm your tutor for today. We'll be treating the topic periodicity and trends. So in some other places you'll see it like the periodic table and trends. So that's what we'll be treating today. And as I said initially, today's lesson would be sticking to time. We'll try to stick to time as much as possible. And I'll try to be as fast as possible, but at the same time, trying to pass the knowledge that is necessary. So let's just head into today's lesson. So today's lesson, by the end of this lesson, we'll be able to explain the development of the periodic table. That's how this periodic table was formed. We can be able to tell for sure how it was formed, can be able to tell the story. We'll be able to understand periodic law, what it means by when they say blocks in the periodic table, you'll be able to understand it, what it means by groups in the periodic table, and also rows in the periodic table. We'll be able to understand it by the end of this class. And we'll also be able to describe periodic trends, stuff like atomic size, electronegativity, ionization energy, electron affinity, and some other ones too. So, and by the end of this lesson, we would also be able to define and identify what isoelectronic species are. So these concepts will become clear by the end of this study. So our mind should be set towards understanding these concepts, so that at the end of this lesson, you can be able to question if you happen not to have gotten any of these ideas cleared. So I'll be trying to break it down and make it as simple as possible while I also take speed. So if you can't hear me at any point, just turn on your mic and speak to me, because I'll not be able to see the chat box. And I think that will be a way that you could use to help me. So let's start with the lesson. So from here, we are trying to talk about how the periodic table was formed and how it's evolved into what we have today. As chemistry students, we all know, we've heard of the periodic table. We've had glances of the periodic table. We might not really know exactly how the structure is or how it was being structured, but this lesson is actually trying to open our eyes and bring it to our understanding how it's evolved from its beginning up until now. So as we have here, I said earlier, attempts to classify elements include the Dobryna's triad. So at the beginning, the scientists have always known that there are stuff like elements. After they found atoms, they were able to divide these atoms into elements or call these atoms elements based on their properties and so on. So when they were able to identify elements and say, okay, this element is known as this element is known as that, so they then tried to see whether there were similarities, rather. They tried to find whether there were similarities between these elements, or probably, because normally, according to scientific principle, normally one scientist, they would always try to observe. The first stage of every scientific method is always to observe. So they tried observing each of these elements to see whether they can find patterns or anomalies. So while they were observing these elements, they were able to find that at some point, some of these elements, they had similar properties. And some of the scientists at that era, they tried seeing whether they could group these elements that were known then into specific forms of groupings. So the initial form of grouping was known as the Dobryna's triad. I don't know if I'm pronouncing it right, but it's Dobryna's triad. So this one, he tried grouping elements in trees. So how he did it was that he looked at elements that had similar chemical properties and also had similar atomic masses. And he said, okay, when we have 3 elements that have similar atomic masses and they have similar chemical properties, that if you group these 3 elements from lowest to highest, the middle element would have a mass that is approximately an average of the two. That is, if you had, we had one element that was maybe 12, that is behave similar with another one that was probably 13, behave similar with another one that was 14. So he said, if we group these 3 together based on their similarities in chemical properties and atomic mass, that once you can be able to group it, that the middle element, once you've taken the average of the masses of this element, the middle element, its mass can be said to be that average of the two on the other side. That's the 12 and the 14. The middle element's mass would be an average of 12 and 14. So such that he can predict, so that we could predict masses of even unknown properties or unknown elements at that time, because then they barely knew many elements. So they just knew the few they knew. They were able to examine these elements and find their masses, find some of their chemical properties. So then these were the determining factors to group elements as similar. So this method evolved according to what we call the law of octaves, or the Newland's law of octave. This law proposed that every 8 elements shared similar properties when elements were arranged by increasing atomic mass. So as to prove that truly, the scientists then, they were very used to observations and also observing similarities and patterns. They, after they had noticed, okay, 3 elements, they started finding that, okay, there is a kind of arrangement that these elements, if we should arrange 8 elements that had, like, maybe one of the elements mass was maybe say 12, the next one was 14, the next one was maybe 17, the next one was 19. If you arrange 8 of those elements that had similar masses, increasing similar masses, that's, if you arrange 8, when you reach the 8th one, the next mass of element that would come next, if you put it back under the first one and the 9th one would have similar properties. So this was how they were grouping it at that time. They were like, okay, assuming we had elements, I would try to simplify it like this, but you would take it as 8. We had element maybe 2, 4, 6, 8. Their masses were 2, 4, 6, 8. So these elements, if they are as we arrange them 2, 4, 6, 8, assuming these were 8 elements, 2, 4, 6, 8 with masses 2, 4. Okay, let me use 1, 2, 3 to 8. 1, 2, 3, 4, 5, 7, 8. Then I said, okay, when you get to number 8, the number 9th element would behave similar to number 1, so that you can repeat the cycle going back to number 1, and you can place number 9th element under the number 1 element. That's most likely they will behave alike. So that was what this law of octaves tried to predict. So this law was very, 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 very close to being perfect, but at some point it was broken as the weights of the masses of these elements began to increase, and this was the basis behind the first 3 periodic tables, the first 20 elements. So the basis behind the arrangement, because it worked very well for the first 20 elements at that time. So when you arrange the first, and arrange second, then going from third, fourth, fifth, sixth, seventh, eighth, 10, then coming back again to 11, 12, 13, like that, they had very similar properties, and their predictions were very correct. But this theory of octaves, or this law of octaves, happened to be violated as we increased the masses of elements. So when this happened, there were still modifications that were being brought up. A scientist named Mendeleev, he also tried to improve the classification by arranging elements in order of increasing atomic masses and smartly leaving gaps for elements that were yet to be discovered. So this guy, Mendeleev, after he had then the recent trend was observing based on increasing masses, just arrange 8, then the next one that will follow, whether you started from the base or not, you just arrange them 8, 8, 8, putting the next one that's following under, the next one that's following under. So, but this Mendeleev guy, he then tried to improve this particular type of classification, and he then said, okay, how would we start from the earliest number of elements we know and try using this octave method. But now we will not just put them 8, 8. Anyone that the mass between maybe one and another one is very far, we will separate them, believing that there is something that's supposed to fill into this gap. We don't know them yet. We don't know these elements. We cannot just say, okay, because the element's mass jumped from, maybe it was moving like 1, 2, 3, 4, 5, 6, 7. Then after 7, the next thing we saw is something like 13, 9, 13, 14, 15, 16. He was like, okay, instead of us just say we would put after 9, we put 13. Instead of us just put like that, let us leave spaces for 10, 11, 12. Probably one day we'll find what 10, 11, 12 is. And here, his own grouping, the thing about his own was that he was grouping it based on their masses. So it's important that if you're writing down, the thing that Mendeleev talked about was, he said how he arranged the periodic table as then was in line with the octave rule. But now he gave gaps for elements that were not yet discovered. But now his arrangement was based on, this was the flaw of his own arrangement, was based on atomic mass. It was based on atomic mass. So take note of these things I just said. He arranged them based on the atomic mass. This was one of the major flaws of his own proposition. He arranged them based on atomic mass. Then he was smart enough. This was a good thing I did. He was smart enough to say, okay, in places where the mass gap was too much, he left space for the ones that were absent. Then he also paid attention to the law of octaves. So this was what actually distinguished Mendeleev out. That most of the time they mention his name when you talk about the periodic table. So because he became very close to the modern day periodic table. The only difference between his own periodic table and the modern day periodic table was that he was grouping it based on the atomic mass, while the modern day theory will see what it groups based on. So now we see at the end of this my page, we said this approach provided a systematic framework that highlighted periodic trends and relationship among elements, paving way for modern periodic table. So as I said, this is pattern and his mode of arrangement actually was an eye-opener that led to the discovery of the normal pattern that the periodic table was supposed to be arranged. So now the modern day periodic table was then discovered by, was then proposed by another scientist called Moseley. So this Moseley, he tried correcting Mendeleev's own mistake. He said, okay, he then discovered
please,
that aside the mass,
the first table, please. I want to screenshot it, please, sir.
the first table, I've not given any table yet. I've not given any table yet. I've not given any table. I've just been explaining so far. So as we have here, was the next improvement that was done after Mendeleev. Mendeleev was very close to being perfect, but another scientist discovered that okay, Mendeleev is grouping it based. He noticed that Mendeleev was grouping it based on the mass number. There is the atomic mass, there is their weight, something like that, their weight. But now he said there is actually a more direct, unique identity that each of these elements have that no other element has. That no element has two. That no element you cannot, because the masses now we could see an element that had mass of 17, and maybe it is called element A. We see another element that has the same mass of 17, but now it's element B. So this kind of grouping was this based on the mass was the error of Mendeleev. So Moseley was able to correct this error by his discovery of what they call the atomic number. And if you remember in one of our previous class, yeah, I remember I was the person that probably taught it then. Not probably, I was the person that taught it, and I talked about atomic number, saying that it is the number of protons. So I remember that clearly, that atomic number was number of protons, and the thing is no two elements have the same atomic number. So meaning that if you see any element having an atomic number of 15 forever throughout the whole of time, only that element, until maybe something happens, maybe later, then we make another discovery. But for now, at the time being, once you see an element that has an atomic number of 15, any other element that you see having the same atomic number of 15 is definitely that first element. You can never see any two elements that would have the same atomic number. So with that going forward, sorry, before I move on, this discovery of the atomic number was what Moseley then did. Then he used the same Mendeleev's principle. He arranged them from lowest to highest using the same similar principles, leaving gaps for the ones that seemed like as if they were too far from each other. So this was one of the breakthroughs to the discovery of the periodic table. So the modern day periodic table is not arranged based on atomic mass. Though on the periodic table that we will see atomic mass above, but what we will see at the bottom is the atomic number. So periodic table is always arranged based on atomic number. Periodic table is always arranged based on the atomic number. The periodic table is always arranged based on the atomic number. So now let's this one was what actually revealed that truly elements, they have a kind of repeating pattern, that they have what they call true periodicity. They had this similar repeating pattern. So moving on, they then proposed what is called the periodic law. Scientists at that time, they then proposed what is called the periodic law. So this periodic law tries to say that properties of elements are periodic functions of their atomic mass. So what does this sentence mean, or what does this law mean? It's saying that elements, any element at all you see, its behavior or its properties is usually linked to its atomic number. So meaning when you see probably an element behaving like a magnet, most likely every element that has similar, that has that same number as atomic number would have the same properties. And these properties can vary in a kind of trending pattern. And maybe this, if they say element, they arrange element A, B, C, D, E, and that's started E, F, G, H, I, J, K, L, M, N, O, P, Q, like that. The ones that are close to themselves, if you arrange them in fives, or if you arrange them in sevens, or if you arrange them in eight, the ones that are close to them would have kind of a fading behavior of the previous one. So meaning that if the previous element had this ability to be very reactive, the next element following it might be very reactive, but not as reactive as the first one. And the one followed down would be kind of less reactive, and so on. That's what it means by the periodicity. They have a kind of relational property, which is a function of their atomic number. So that's what the periodic law is trying to explain. And these elements show similar properties at regular intervals when arranged by their atomic number. So this particular portion of the periodic law that states that elements show similar properties at regular intervals when arranged by atomic mass was the basis behind the octave law then, because they noticed that they were behaving similar, and because of that, when they reach a particular, maybe they arrange element A, B, C, D, E, F, then they now know that after F, G does not even behave anything close to F. They would say, okay, since it doesn't behave anything close to F, that means it means at the end of this line has cut here. So let's look for whether it behaves similar to A that we started with. So they will now take it back to A and say, okay, it behaves similar to A. And usually that is actually mostly true in most of the cases. So these were the basis for the periodic law. The periodic law states that properties of elements are periodic functions of their atomic mass, and elements show similar properties at regular intervals when arranged by atomic number. So these first two lines here on my slide, they are what is known as the periodic laws. So the first two lines are the periodic laws. So this law, it underpins the structure of the modern day periodic table. So what this is saying is that based on these two laws, based on the understanding of these two laws, they were able to generate what we now see and know as the periodic table. So with that being said, I believe we now know what periodic laws are, and with time we'll be able to memorize them individually at our own pace. So now let's move on to our next slide. So after we've known that they were able to create what we call the periodic table, we know the periodic table is an arrangement of elements based on their increasing atomic number and repeating similarities in behavior. After this, we've known that, okay, they've created what they call the periodic table, which is that arrangement. This table was not just created just haphazardly. It was created and they gave special details to different sets of elements. So these special details led to the formation of what we call blocks on the periodic table. So on the periodic table, we have just, pardon me, we have just four blocks of the periodic table. So mean anywhere you go, as at the time now, as at today in existence, we have just, to the best of my knowledge, we have just, we have just 4 blocks of the periodic table. We have just 4 blocks of the periodic table. So when I go to the image where we see the periodic table, at least I believe it should become clear when I'm saying this now. Repeat most of these things I've said when we reach the periodic table, so that we'll be able to recognize most of them by looking at the periodic table. So we have 4 blocks of the periodic table, and these 4 blocks are S, P, D, and F. S, P, D, and F. S, P, D, and F. So these 4 blocks, they have the reason for their grouping was based on how close these elements they behaved alike, based on the research. that scientists do, and they did, and the experiment that they carried out. So based on these their experiments and their findings, they were able to group all these elements then in blocks. So we then they then group them based on 3 blocks, the S blocks, and they gave each of these blocks, they gave them names as letter S, letter P, letter D, and letter F. And these SPDF periodic groups, or these blocks of the periodic table, they have total number of it's actually based on the valence electrons, this SPD and F. Pardon me, please. This SPD and F was grouped based on some kind of reactivity and similarity in behavior, and also to some extent the level of valency on each of these electrons. So I remember that I said valency in our last class. I said valency is the number of electrons in the outermost shell of any element. Is the number of electrons in the outermost shell of any element. So now, if an element has 1 electron in its outermost shell, any other element that has 1 electron in its outermost shell, they will be grouped under the same portion on the periodic table. But now, this periodic table, now they answer, okay, the S block of the periodic table would contain only elements with just only 2 types of elements. Only 2 types of elements. That's elements that have just 1 electron in the outermost shell, and another element that have 2 in the outermost shell. So these 2 blocks are what make up the S block of these 2 groups are what make up the S block of the periodic table. So the S block of the periodic table contains element that has maximum of 2 electrons in their valence shell under normal condition. So the S block contains elements that have maximum of 2 electrons between 1 and 2. Their electrons are between 1 and 2, but it cannot exceed 2. Once they exceed 2, it's no longer called an S block element. So the S block element has a maximum of 2 electrons, and they have a maximum of 2 electrons, and it contains that 2 electron corresponds to 2 groups that they have electrons 2 maximum in their outermost shell, or 1 maximum in the outermost shell. So we have elements from number 1 and 2. Sorry, 1 and 2 electrons at the outermost shell. They are grouped under the S block. But later, this grouping, we will see how this grouping probably relates to orbitals. But let me just hurry up because we're talking about the periodic table. So we have 4 blocks: the
Hello, sir.
S block, the P block, and the D. Yeah.
You said that
Hello. 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 Can you guys hear me?
yes, I can hear you,
Yes.
sir.
Okay. Probably it's a network that is disconnected from talking. So we have the S block, the P block,
Yes,
and
I've
the
started
S.
hearing you. I said, you said that
Okay.
in S block that it contains maximum of 2 electrons, and the electrons
In the
corresponds
outermost
to what?
shell.
And the outermost shell,
Okay, they
and the
have
electrons
maximum of the electrons there. It's with respect to
corresponds
their
to what?
outermost. It corresponds to the orbitals of this electron, but that's not for the scope of this study. We are not talking about orbitals for this study. We're just talking about the periodic table and the blocks of the periodic table. So these electrons, the number of electrons corresponds to the orbital, the last orbital of each of these elements. But I don't want to complicate everything because we're just focusing on the periodic table. So I will not go into that detail. But this S block, SPDF, relates to orbitals. Just know that one at the back of your mind. It relates to orbitals. But these SPDFs are the same blocks, in the periodic table. So the SPDF, for the S orbital, it contains 2 groups. It contains 2 groups, while the P orbital contains 6 groups. The P orbital contains 6 groups, and the D orbital contains 10 groups. The D orbital contains 10 groups. The D orbital contains 10 groups, while the F orbital, Sorry.
Jesus.
Please, if your mic is on. If your mic is turned on, please help us turn it off so we would not get distracted.
Somebody.
Okay, so let's continue. As I was saying, the p orbital contains 6 groups. The d orbital contains 10 groups. F orbital contains 14 groups. So from what we have on the board here, I said group 1 and group 2 elements are under the S block. Group 1 and group 2 elements are under the S block. Then also group 13 to 18 are under the P block. So when we go to the periodic table, I'll show you why they call it group 13 and to 18. Some places you will see it group 3 to 8, but it will say 3B to 8 or 3A to 8A is under the P block. That's what they will say in some places. But in some other places, they'll tell you group 13 to group 18 is under this. So with that being said, just take note that group 1 to 2 is the S block. Group 13 to 18 is the P block. Group 3 to 12 is the D block. Group 3 to 12 is the D block. Then, then the F block was extracted from some part of the D block. The F block was extracted from some part of the D block. So how they brought out this F block was that they said, okay, there were some sets of elements that they behaved very, very similar. And based on their orbital stuff, when we get to orbital, we'll be able to explain it then. But for now, these elements, I will keep it as the knowledge that they behave very similar, and putting them in the periodic table under the D block would not fit well. So because of this reason, they had to separate them and give them a separate block called the F block. So the F block is part of the D block, but it has completely different behavior from the general D block element. So they had to remove it separately and call it the F block. So this F block is also known as the block containing the lanthanides and actinides. From what we can see even on my screen, I said F blocks are called the lanthanides and actinides, while the D block is called the transition metals. The D blocks are called the transition metals. Group 1 and group 2 is called the alkali metal and alkaline earth metal. Alkali metal, aka Li, alkali metal. That's group 1. While group 2 is alkaline earth metal, aka Line. Then they now said earth metals. So in simple description, they will call them soft metals. The both of them. They'll call them the soft metals. Then the P block is combination of some metals, non-metals, and metalloids. It's made up of some metals, non-metals, and metalloids. So this is actually the contents of each of the blocks of the periodic table. So hopefully in our next slide, we should be going to the slide where I kept the periodic table. So we'll see how it looks like. Probably by then, these things I'm saying will be more visual to you guys. So now we can see here, leave the letters we are seeing inside this periodic table. They are not exact. They are not correct. So you're seeing TH here, you're seeing PA here. It's not correct. Just look at the overall structure. It's not really even correct. The structure of this element, this periodic table is not correct. I'm seeing 3 here on this our left hand side. I'm very sorry for this. I did not observe this stuff. I didn't observe it. I would have not used this table, this image. But the standard periodic table is containing at this point here, at this top here, we have just 1 and 2. That's the S block. The first blocks you always see on your left hand side. The first 2 groups you see on your left hand side, and the first block of that left hand side is called the S block. Then when you come to this end here, you will see from this place, you see something like 6, not something like, you will see 6, specifically 6 other groups, 1, 2, 3, 6 other groups that make up the P block at this region, from this end to this end. From this end to this end, you see 6 groups. If it's not 6, no, you are not drawing it correctly. It's definitely 6 on this side, 2 on this other side. Then at the center, you would have compulsory 10. 2, 10 at the middle, 6 at the end. 2, 10 at the middle, 6 at the end. So these are the arranged, they always arrange it like that. You put 2 up, 2 at the extreme, left extreme. They call those 2 the S block. The middle, we have 10, and they call that those 10 the D block. Then at the extreme right, we have 6 blocks, and those 6 blocks are called the P block. So then on that, we then have this one. I'm seeing 3 rows. 1, 2, 3. It's not 3. It's actually 2 rows. So I'm very sorry for this image that is looking like this, but you can download. You can go online and download your standard periodic table. You will see a standard periodic table, and to look more true than this. But I can tell you that this is not correct. Completely is not correct. I'm very sorry for this oversight. So with this now, the F block contains 14 rows. Sorry, 14 columns. So what I mean by 2, 6, 10, 14, what I mean by this is when you are counting the number of columns, if you know columns are vertical arrays. Vertical arrays, like moving from up down is a column, from up down is another column, up down another column, up down another column. So the number of times they are moving up down, up down, up down, they are the number of columns. So on this F block, we have 14 of up down movements throughout the whole length of the F block. So we have 14. On the D block, we have 10. So this up down movement, that's the column. We will know what they are called, but normally we're supposed to know what it's actually called groups. So in each block, take note, in each block of the periodic table, there are groups that make up the blocks of the periodic table. Okay, so let me take it slow a bit. We've talked about the S block, the P block, the D block, and the F block. And I said, if you're writing on your notes, just write S block, 2 groups make up the S block. 2 groups make up the S block. Then the P block, 6 groups make up the P block. 6 groups make up the P block. Then for the D block, you would write 10 groups make up the D block. 10 groups make up the D block. Then for the F block, it is 14 groups make up the D block. 14 groups make up the D block. So that's just like a summary of everything I'm trying to say. We have on the periodic table 4 blocks, and each of these blocks have number of groups that they contain. I just explained the number of groups that each of them contain. S contains 2, P contains 6, D contains 10, F contains 14, and these things, they are constant. So you just memorize it. You don't need to say, okay, maybe it will change later. They are constant. S would always be 2, P would always be 6, at least for the best of my knowledge. P would always be 6, D would always be 10, F would always be 14. So that's actually how the periodic table is. So you could go to your maybe browser, or maybe later on I'll find a way. Maybe I'll send something like the image of the real periodic table to you guys. I always say I'll send something, but I'll later forget because of my the nature of my my work. I always most of the time I always forget. So it's actually that I just explained now. We have 4 blocks. Each of these blocks have number of groups that they contain. So that's actually summary of the periodic table, what it looks like. So moving on to the next slide. I hope I've explained, I've summarized that explanation now. I hope I've been able to summarize that explanation.
Yes, but from that blocks, those diagrams, you said oh, here's this, I didn't understand it, but I understood what you explained. But from the blocks they gave there, you can use your cursor to point it, please, sir.
Okay, this block, this one I gave here is not really correct. That's why I'm not really trying to dwell on this diagram, because instead of me trying,
I know, just to know how the blocks, because I can't visualize it.
Okay, S is at the extreme left. The 2 that will be standing tall at the extreme left is the S block. The 2 that will be standing tall at the extreme left is the S block, while the 6 that will be standing tall at the extreme right is the P block. The 6 that will be standing tall at the extreme right is the P block. While the 10 that will be at the center, that they are short, they are not really tall, they are short at the center, there are 10 of them. They are known as the D block.
But I counted it. It was it is 11 blocks there.
That is.
Yeah, that I said this diagram is not correct.
That is what. Did you know here that the thing is not correct? Ah.
Okay.
Is it me?
Okay.
Okay. I said that when I was importing this, because I was trying to I was juggling between several stuff while I was preparing this slide. And when I knew that this is what the periodic table looks like, I just imported it into this slide. I did not observe. That was my bad, and I'm very sorry for that. So this block is not correct, but just know the idea that we have the S block at the extreme left. Oh, sorry, at the extreme left, yeah. The P block at the extreme right, then the D block at the center, then at the bottom is where you see what they call the F block. And each of them, they contain 2, 6, like that, number of groups. So we are good to go, right?
Yes.
Okay, so let's head on to the next slide. So now, I was saying groups on when we're talking about the periodic table. So now, I'll be trying to explain. I've already explained it preliminarily. And I said groups are the vertical arrangements of elements. Groups are like the vertical arrangement of elements. So when you are moving from up downwards on the periodic table, from element up down on a straight line, that is called a group. From up down on a straight line on the periodic table is called a group. Everything that is on from up down on a straight line is called a group. A column is called a group. That was what I mean by up down. It's also called column. A column, each column of elements is called a group. While if you move from left to right on the periodic table or right to left on the periodic table, that movement left and right, the arrangement of elements from left and right horizontally is what they call period. So let me go to the previous slide so we'll see what I mean. So going down like this, from see my cursor here, up, going down is called going, that's a group. This is another group. Here is also another group. Here is also another group. Here is also another group going down like that. So these are groups going from up down. So when you talk about period, period is like this, moving from left to right on a straight line, from left to right on a straight line. These are periods. From left to right on a straight line. These are another period. From left to right on a straight line, left to right on a straight line. So that's the difference between periods and groups. Groups are vertical arrangements of elements, while periods are horizontal arrangements of elements on the periodic table. So now, on the periodic table, you would always see, for a standard periodic table, we always see 18 groups, as I said. There was a point I said we have 18 groups. So now, before I forget, I know I was saying something about in some tables, you will say, or some people will say group 1 to group 8 is what is on the periodic table. So why they say group 1 to group 8 is because they just count only the S block and the P block. They add just the S block and the P block. When they omit the D block, that's when you have group 1 to group 8 as the periodic table. But when you include the D block, the D block is 10. So that D block stays in the middle. So when it stays in the middle, it will then shift. Instead of this place, let's assume it was 1, 2, the next one supposed to be 3. Because the D block comes to occupy the space of number 3, every other one that was there before the D block will shift. Then they will start giving them number until they get that one that was there before they will give it its own number. So normally an element that the former element that was maybe number 1, number 2, number 3, number 4, from number 5, the former element that's supposed to be number 5 supposed to be, we have hydrogen, helium, lithium, beryllium, boron supposed to be number 5. But that's when you don't include the periodic table. When you don't include the D block, boron will be number 5. It will be on the 5th group. But when you then include the D block, it cannot be said that boron is on the 5th group of the periodic table. It is on the 5th. Is it 15 that I'll call it? This is going to be 1, 2, or to be on the 13th group of the periodic table. what was I saying? Sorry, boron is supposed to be on the third group of the periodic table. Hydrogen, helium, lithium, beryllium, boron. Yeah, supposed to be on the third group of the periodic table if you don't put the D block. So what do I mean by that? And in case of, I really apologize for this error in this image. Just ignore this middle one, this one here. Ignore it. Ignore it. Don't look at it as there are 3 here. Just take that there are 2 here. Then we have 6 at this end. So normally, if you did not put this center D block, these low ones, if you don't put them, you'll be having 1, 2, 3, 4. This one's supposed to come next as 5, 6, 7, 8, like that. That's supposed to be arranged. But now, if you then put this one, this will be group 1, group 2, group 3, group 4, group 5, 6, 7, 8, 9, 10, and this will be around 13, 14, 15, 16, 17, 18. But if this D block is now among, we're having 1, 2, 3, 4, 5, 6, 7, 8. I don't know whether it's clear. So when they don't include the D block, you'll just be having 8 groups of the periodic table. But when you include elements of the D block, you'll be having a total of 18 groups on the periodic table. So just take note of that one. Probably in our next class, I'll try to bring a correct periodic table and try to explain this thing again. So to cover up for this mishap that happened. So let's come to the groups and periodic table, groups and periods, as I was saying. We have on the periodic table, we always have 18 groups, and we have 7 periods. Mostly, there are always 7 periods and 18 groups. Take note of this: 18 groups and 7 periods. 18 groups and 7 periods on the periodic table. And the elements in the same group have similar chemical properties. So now we're not trying to see the similarities between the groups and periods. So elements in the same group have similar chemical properties. So meaning that if an element, if we have like 5 elements in group 1, all of them would have similar chemical properties. If you have 3 elements in group 2, all 3 elements in group 2 will have similar chemical properties. So take note that I did not say physical properties, I said chemical properties. So the similarities in their chemical properties. And the reason for this similarity in properties is because they have the same number of valence electrons. So all these points I'm mentioning, I would like you to just be writing them down on one, maybe your jotter that you're using to write down. So the ones that are important that I feel that are worth taking note, I would call them out. So it's important to know that we have 18 groups on the periodic table, 18 groups on the periodic table, and also to know that we have 7 periods on the periodic table, 7 periods on the periodic table. And also it's important to know that elements in the same group have similar chemical properties. If it means for you to underline chemical properties, for you to know that there's an emphasis on chemical properties, just underline it. So they have elements of the same group have similar chemical properties. Same group, similar properties. Same group, similar chemical properties. And the reason why they have this similarity in chemical properties is because they have the same number of valence electron. They have the same number of valence electron. So you might see it as a question. If I were to be probably an examiner and I want to say this question, I would like to say something like this. I would like to ask this kind of question: that why do elements of the same group have similar chemical property? The answer is just simply because they have the same number of valence electron. You could see it in your exam. I think I've seen something like that in different exams. I don't know about JUPEB, but in different exams, I've seen questions on this kind of thing. So the reason why they have similar chemical properties is because all elements in the same group have the same number of valence electrons. Same group, similar properties. Same group, same number of valence electrons. Same group, similar properties. Same group, same number of valence electrons. So these are the 2 things I just mentioned now. So now, properties change gradually across the period. So this is what I was saying at the beginning of this class when I was talking about the octave rule. They said if you are moving from left to right when you arrange elements in a particular increasing order, you notice that a particular property would begin to fade off as you move from left to right. Probably if a particular element had maybe strong electricity, the next element following it will have strong electricity, but it will be less than that first one. The next one following it will have a faded level of conductivity for electricity, and so on. It's keep on reducing from left to right. Properties always vary. Their properties change from left to right, that is across the period. Properties of elements change across the period. So these are now important points to know about the periodic table. The properties of elements change gradually across each period. And the reason for this gradual change is due to the increasing nuclear charge. Increasing nuclear charge. That is the reason for this gradual change in property. Because as you go from left to right, their nuclear charge is increasing. The nuclear charge is increasing. So these are important take notes that you should take or you should have in regards to the periodic table. First, that there are 18 groups of the periodic table and 7 periods of the periodic table. Next, same group of elements in same group have same chemical properties, or similar, not same, similar chemical properties. Elements of the same group also have the same valence electron, the same number of valence electrons. Then also, the properties of elements change as we move from left to right. It changes gradually as you move from left to right across a period. As you move from left to right, the properties of elements change gradually. So I'm mentioning properties, I'm mentioning change, and I'm mentioning gradually as you move from left to right. Properties change gradually. Properties change gradually as you move from left to right on the periodic table or as you move across a period. And the reason for this change is because of the nuclear charge, the increasing nuclear charge. So what does it mean by increasing nuclear charge? We said that they are arranged elements based on the atomic number, and atomic number corresponds to number of protons. So as the number of protons is increasing, the charge of the nucleus is also increasing. And as the charge of the nucleus is increasing, the properties of elements begin to fade from the previous ones. So later on, we would probably make a more visual explanation of this stuff. So let's move on to one of the general characteristics of elements or trends in the periodic table. So when you talk about trends in the periodic table, they would always talk about atomic size.
Sorry, excuse me,
When you
sir.
hear,
No vex.
yeah, I'm listening.
You said
Yeah, I'm
that
listening.
if the charge increases, what will happen?
If the as you move from as the number of protons increases, the charge on the nucleus begins to increase, become more positive. So then now, as the charge is increasing now, it will then be causing the properties to begin to fade. Similar properties, probably a property that was very pronounced in the first element will start fading off gradually as you move, as the number of charges increasing, the number of nuclear charges increasing. The property will start fading gradually. So it's just like as if you're trying to say you carry them, people have different, everybody has a bottle of water. So everybody has a glass cup of water. Or if everybody has different quantity of water filled in the same size of glass cup, maybe one person filled 1 mil of, or 1 mil, yeah, 1 mil of, or 100 mil of water in his own cup. The next person filled 200 mils of water in his own cup. The next person filled 300 mils of water in his own cup. The next person filled 400 mils of water in his own cup. So now, if you want to color each of these cups with maybe, say, 50 mil of water throughout, you tell everybody, take 50 mil and pour inside your cup. The person that has lowest amount of water, when he pours that color, maybe Zobo, inside his own water, it will become dark. But the person that has higher number, that has maybe from 100 mil to 200 mil, the person that has 200 mil, when you pour the same quantity of Zobo, his own will be dark, but not as dark as the person that just had 100. When you go to the person of 300, when he pours, his own will fade, it will begin to fade. So this is how the trend is increasing. As you move from left to right, the trend, that is the properties of these elements begin to fade off as their nuclear charge is increasing. So just this analogy is just trying to tell, the increasing size of water is showing the increasing nuclear charge. So as you move from left to right, those properties that are supposed to be the same throughout will begin to fade as the nucleus charge increase. I don't know whether I explained this clearly.
Yes.
Okay, thank you. So it's just like as if everybody say, oh yeah, everybody take cup of water and we want to make tea. Then everybody say, yes, let's make a cup of water. One person took a small cup of water. Another person take a bigger cup. Another person take another bigger cup. Another person take the biggest cup. Then they say everybody, I'm giving everybody one cup of milk and 3 cubes of sugar. The person that has the lowest quantity of water, his tea will be sweeter. The next person that will follow him is the person that has the next small quantity of water. It will be sweet, but its own will not be as sweet as that. It will be the sugary taste will start fading as you move, as the number of water increases. So that's just what they are explaining in that sentence, that the properties will keep on fading as the nuclear charge is increasing. So that's the analogy I think is the easiest way to explain this stuff. So now, moving on to atomic size. So when we talk about trends in the periodic table, they usually talk about atomic size, and they can call it atomic size or atomic radius. So it's still the same thing, talking about the size of atoms. So this atomic size is the distance from the nucleus of the element to the outermost electron. So now, just like this, now see this diagram that we have by my right. By our right, you see this electron here, this center, this big ball at the center. If you want to check the size, if this was an element or this was an atom, this is an atom, the size of this atom, it will be the distance from this place, from the center to the outermost electron. If you want to tell the size of an atom, you will check the center atom, the center of that atom to the outermost electron. There might be electron in this inner side, electron in this inner side, electron in this inner side, but the outermost electron, the distance between the center and the outermost electron is what they call the atomic size, and is also known as the atomic radius. So this size is said to decrease across a period. So I don't know, you guys remember when we remember the principle that said like poles repel, unlike poles attract. Like poles repel, unlike poles attract, meaning that positive and negative would always attract. Negative and negative they will not attract. So now this principle of like poles repel and unlike poles attract, it plays in atoms. I remember one of the classes, someone was asking me saying, why is it that as the electron, the number of protons in the element, why is that upon their protons positively charged in the nucleus, the electrons, it does not draw the electron inside the nucleus because they are close? Why is that it does not, the electrons don't come and join, since unlike would always attract? Why did the positive in the inside not draw the negative to come inside? And I said it was because of a shielding effect. There was not like a blanket that's covering the ones inside that said the electrons cannot do anything but stay outside that place. So now, as the number of positive charge inside the nucleus starts increasing, their influence on the outermost electron, that is mean the number of positiveness will now be increasing, meaning that every negative will start drawing, the force of the positive will become stronger than that nuclear force, will start becoming strong enough to draw more electrons towards itself. So because of this pull, as the nuclear charge increases, the atomic size is known to reduce because of this pull from the center. As the number of protons at the atomic charge increases, the nuclear charge increases. So because this nuclear charge is increasing, the size of the atom begins to reduce. It's just like as if we are doing all this tug of war. Let's say we are doing tug of war now. We have 3 people inside the center. 3 people are inside the center. Then we have people outside. Maybe we have 3 boys inside the center. Then we have maybe 3 girls outside. 3 boys inside, 3 girls outside. So now, if the number of boys inside, let's say let's say 3 girls inside, 3 boys outside. The girls are trying to pull the boys inside their cycle, but the boys are strong, they're staying outside. So there's a tension between them. So now, as the number of girls, as I say, more girls should join inside at the center to come and help the girls. As the number of girls keep on increasing, they will be able to draw the guys closer to themselves. They'll be able to draw the guys closer to themselves, to their center. So as they're drawing the guys closer to themselves, they are shrinking the distance between them and the guy. And that's why they say atomic size reduces as the nuclear charge increases. Atomic size reduces as the nuclear charge increases. And what does it mean for nuclear charge to increase? As you move across the period, the nuclear charge is increasing. So as the nuclear charge is increasing, it means that the pull of the nucleus on electrons outside will become more, and this atomic radius will begin to shrink more and more, leading to a reduced size in atom as you move from left to right. I don't know whether this explanation is clear. Do you understand what I'm explaining?
No, sir, please, can you explain the second one? This decreases across a period.
Okay, we know what periods are. Periods are just moving from left to right. And we said that in the periodic table, we always arrange them in an increasing order from left to right. So it's just, I'm just saying that in the periodic table, we would always have 1 starting from this side, 2 next, 3, 4, 5, 6, like that. So now, as we move from left to right, what is happening? We're increasing 1, 2, 3, 4, 5, 6, 7, 8, like that. We are increasing. That 1, 2, 3, 4, 5 that is increasing is the nuclear charge that is increasing. So as the nuclear charge is increasing, it means the strength of the nucleus to pull electrons towards itself is increasing more. So it is having more strength to pull its electron towards itself. That is, the number of girls in the cycle is increasing. They will be able to draw the boys closer to themselves. And that gap between the boys and the girls will start closing in. It will start closing in. And because it's closing in, the size of the electron will be, the size of the atom will begin to shrink. I don't know whether it is clear. I don't know. Is it clear now?
Yes, sir.
If it's not clear, please tell me. Let me see whether I can find another explanation, or let me just give one last explanation. Let's assume we had they tied everybody. They said everybody should stay at one spot. They held everybody. They said everybody stay at one spot. Then they now had one cow to be pulling people. The cow should be trying to run away. Then the person at the center is pulling the cow, but there's something that is blocking the person, that is not allowing the person to go outside, that the cow should not draw the person. Something is holding the person so that the cow cannot go run away. The thing is holding the person very strong. So now, as people will start coming more to come and join that person to pull the cow, they will be able to draw the cow closer to themselves. And that distance now, the size of the distance between them and the cow will begin to reduce. And that size between them and the cow is called the atomic size. So as the number of charges of the nucleus increases, so does the atomic size reduce, because there are more forces that is now pulling electrons inside. So since they are pulling the electrons inside more, it is now making it that the distance is reducing. I don't know whether I'm passing any information. I don't know.
Yes,
Yes, sir.
Okay, thank you so much. So I believe that one is clear, that it said as we move across a period. So if you want to write it to simplify this whole thing, you say as you move across a period, the nuclear charge increases. Then you can put maybe from 1 to 10, put brackets closed. Then I say as this nuclear charge then increase, the atomic size would reduce, because the force on the nucleus, the force in the nucleus has increased, so you can pull more electrons to itself. I don't know, you can put it in your terms, but the main thing is you are moving from period down to the size. But now, what is making the period, as the period is increasing, we are moving from left to right in the period, the nuclear charge is increasing as well. And as the nuclear charge is increasing, it will now be causing the pull of electrons on that period to be more. They will be reducing in size. So meaning that in the periodic table, the biggest size on the periodic table will be at this end, will be at the left. The next biggest one will be at the next one following it. Going down, as you're moving from left to right, the size will be reducing continuously in the periodic table. Meaning that on the periodic table, typical in the periodic table, we have lithium, hydrogen is on the left-hand side, helium is on the extreme right. Then we have lithium. Lithium size will be bigger than beryllium. Beryllium size will be bigger than boron. Boron size is bigger than carbon. Carbon size is bigger than nitrogen. After nitrogen, oxygen will be smaller. After oxygen is smaller, fluorine will be smaller. After fluorine is smaller, neon will be much smaller. So that's how the atomic size moves across a period. It continuously reduces across a period. So that's for atomic size. So they said when you move down the group, as you then move down the group, the atomic size is going to be increasing. So across the period, it is reducing, but down the group, it is increasing. Down the group, it is increasing. And the reason for this increase down the group is because as you move from the top of the period, coming down, the number of shells are increasing more and more. That is the number of this cycle. The inner cycle is for period 1. The next cycle is for period 2. The next cycle is for period 3. The next cycle is for period 4. Like that. That it keeps on going. The cycle, each of those cycles, as the cycles are increasing, definitely, as you're moving from up to down, the cycles are increasing continuously. And as these cycles are increasing, it means that the size of the atoms is also expanding continuously as you move from up to the bottom. I don't know whether it's clear.
Yes, sir.
Okay, thank you. So take away. As you move down each group, atomic size reduces because of increase in number of shells. As you go down the group, I'm repeating myself, as you go down the group.
I thought you said that as you move down the group, it increases due to addition of
Yes, I
electrons.
said not due to addition, not due to addition of electrons, though partially due to addition of
Addition of
but not
electrons.
necessarily due to addition of electrons, but it's due to the increased shell. As the shell increases, as the electron shell increases, the size is increasing. So that's
That
the
one
reason why as you move
moving down the group now.
yes, that's moving down the group. So then moving across a period, it is the reverse. As you move across the period from left to right, the atomic size reduces. And the reason why it is reducing is because of increasing nuclear charge. So I'm giving you a trend, and I'm giving you the reason for that trend. So I'm saying moving down the group, atomic size increases. That's the trend. And the reason for this increase is because of the increased number of shells as you move down the group. While as you go across the period, atomic size reduces. That's the trend. Atomic size reduces. So the reason for this reduction is because of the increasing nuclear charge. So that's for atomic size. I believe that should be clear for now. So we can move on to the next slide. So we'll not spend much time. Let me see how much I have. How much time I have here. Oh God, that time is just running. So I think, let me see.
Time flies.
So now let's move on to the next slide. Let's see how much you can hurry. So we have electronegativity. So from what we are seeing here, I said electronegativity is the ability for an atom to attract electrons to itself in a chemical bond. So take note of in a chemical bond. In a chemical bond. So you will not talk about electronegativity when there is no bonding. You will not talk about electronegativity when there is no bond between an atom and another atom. So when you have one atom, maybe atom A, bonding with atom B, you can then talk about electronegativity. So and now that electronegativity is now the ability for any of the electrons to be able to pull electrons towards itself. You know that they said every bond has electron that they use to form it. So this electronegativity is just like as if you're saying, okay, well, everybody has money. But when you and somebody come and join together to do a business, that's you bonded, that person usually steals your money more. He benefits from you more. He takes more of your money. So that ability for the person to be able to steal more of your money is called the electronegativity. The ability for atoms to be able to draw more electrons towards itself when there is a bond. That is when it is bonded with maybe atom A bonded with atom B, then they're supposed to be sharing the electrons equally. But now atom A now has a high level of electronegativity. It means it will be drawing the electrons towards itself. So A will now have few electrons towards itself, while A will have more electrons towards itself because it has strong electronegativity, while B will have few electrons on itself because the electronegativity of A is more than that of itself. So it's like as if as the electronegativity increases, the bully nature of each element become more, of each atom, sorry, becomes more. They begin to bully the other one that they are paired with. So maybe they give everybody food, maybe they'll give everybody three plates of food. The one that is more electronegative will say, okay, give me your own. Give me your own. Just bring two of your plates. Hold only one. So that's how electronegativity works. It pulls electron. It is that ability for a particular atom to pull electron towards itself in a chemical bond. In a chemical bond. In a chemical bond. So that's electronegativity. So now, this one now, they say it increases as you move across a period. It increases as you move across a period. So from when I was explaining why the size of atoms reduce, when I was explaining why size of atoms reduce in the periodic table as you move from left to right, I said because of the nuclear charge is increasing, so the nucleus can draw more electrons towards itself. So meaning that this same trend, this same ability to draw more electrons to itself is telling us that electrons that are towards the other end, electrons that are, as you go down the period, as you go across the period, as their nuclear charge is increasing, they have more tendency to pull electrons to themselves. So meaning that even if they bond with another element, they would also pull that same element's own electron towards themselves because they have strong core. They have strong core. Because of this strong core, they have higher tendency to be more electronegative. So that is the reason why fluorine is highly electronegative. If you bond fluorine and oxygen, fluorine and hydrogen, it would displace all the electrons towards itself. If you bond chlorine and hydrogen, it will pull all the electrons towards itself. If you bond all those elements at the end of the periodic table, the right end, they are more electronegative because the number of charges in their nucleus is higher than the ones towards the right. So because of this high level of core strength, center strength, they can pull more electrons towards themselves. So that's why they said electronegativity, it increases across the period. I don't know whether this is clear.
Yes,
Are you guys following?
We have.
Yeah.
Yes,
The
ma'am.
you gave concerning
Someone
atom A bonding with atom B. Please, can you repeat it? It's a good one.
Okay, let's assume now we have teacher and students. Let me use that one. Probably you guys are the students, then probably I'm the teacher in this case. If anytime that they say teacher and student should sit down together, if they want to give food in party and teacher and student went, they will definitely give the teacher more food than the children. They might give the students small food, but the teacher's own size of plates will be bigger because they believe that these teachers have more strength or they have more capacity than the students. The students cannot talk, but teachers can talk about that. This school they are bad. This school they are. So they believe that these teachers they have more capacity. So that's how they treat electronegativity. Elements that are more electronegative, when they stand with another element that is less electronegative, they would draw that element's own glory towards themselves. So if I want to use Nigerian diabolical, I'll call it spiritual point of view. Someone that has let me leave that story. Let me leave that one for another time. So it's just like when we have someone that has strong tendency, like he's stronger, he has a strong appearance in public. If you stand with another timid person, people will focus more on the person that is. Hey, let me use girls and boys now. There are some people that they say, okay, girls like guys that are muscularly built. So now, if a slim guy stands beside a huge guy, girls would go towards the huge guy more than the slim guy. So that's just what's happening. When you have two friends, a guy that is slim and a guy that is muscular, the guy that is muscular, even the guy that is slim, his girlfriend will be liking the one that has muscle because they believe that muscular guys are more protective than slim guys. So they would want to go towards the muscular guy because if something happens, the muscular guy can save me, but this my slim guy, he no go fit help me. So that's just the same thing that happens when it comes to electronegativity. Two atoms will stay, and one of them has that tendency to be more electronegative, have more nuclear charge in the center, is stronger in its nucleus. So because of that reason, when we then bring these two atoms together, electrons would prefer the one that has more positive than the one that has less positive. So that's just the idea of electronegativity. I believe it's clear now.
Yes, sir.
Yes, sir.
So that's just how it is. So in a simple level, it's just like as if the nuclear charge is money. So the guy that has more money and the guy that has less money, the sad reality is that when this guy that has less money and the guy that has more money stands, when girls come, they would go towards the guy that has more money. So the guy that has more money is more electronegative than the guy that does not have money because he has more money. His more money is like talking about his nuclear charge. So as his nuclear charge is more, he would pull more girls towards himself, even if he's not as fine as the other one, but he will pull more ladies to himself because of his inner charge, because of his inner pocket, that kind of thing. So let's focus on what we have here now. So with this now, we can see why they said as we move across a period, the electronegativity increases because the nuclear charge is increasing as we move across the period. The money that each of the elements are having as you go across the period is increasing. And as their money is increasing, it means that the ability to draw more females to themselves is more. So I believe that analogy should be clearer to everybody. So now let's move to down the group because of time. Going down the group now, I said, as you go down the group, because of the increased distance. Okay, this sentence is going to be kind of complex, but from what I have here, I'm just going to read it out first, then I'll then explain what it means. They said the electronegativity decreases down a group because of the increased distance and shielding. So now, what this thing means is this. We say that as you go down the group, shells, the shells of electrons, sorry, the shells of atoms, they have their shell, the number of shells increases. It's just like as if the person that now, as you go down the group now, someone that is locked inside one room can see outside faster. But when he's locked inside one room and locked inside, and that room is locked inside another room, and that room, so he can barely shout out to call people towards himself. So that's the same way. When you have a nucleus that many shells have covered it, that nucleus would, even if it is strong, it will barely be able to attract any electron because of the different shells that are blocking it. I don't know whether it's clear. We have somebody that is very strong, but now we have, as it's very strong, they use different layers to cover it, So no matter how strong it is, these layers that are covering it would make it seem like as if it is not weak. Like as if you have a magnet now. If you leave that magnet open, the magnet can attract every metal around it. But when you keep on wrapping that magnet with wrapping it with more wrapper, the wrapper is representing different shells. Wrap it with one wrapper, it can still magnet to some extent. Wrap it with another wrapper, the magnetivity would reduce. The magnetism, would reduce. So the more you cover this nucleus with more shells, they call it shielding. The more you cover the nucleus with more shells as you go down the group, the weaker the nucleus will be to draw electrons towards itself. And the drawing of electrons is the electronegativity. So since you are covering it more, it will have lesser ability to draw. So the electronegativity is said to reduce as you go down the group. So I don't know whether that one is clear too.
Yes, it's clear too.
Okay, so as you go down the group, electronegativity reduces because of the covering on the nucleus. So the nucleus is supposed to be an attractive entity. But now, the more you cover this nucleus, as you go down the group, the first one on the group has just one covering. The next one has two covering. The next one has three covering. The next one has four covering. So the person that they cover with one cloth can easily come out and draw electrons itself. But the one that has covering of like 4 would hardly be able to draw electrons towards itself. So that's why they said electronegativity seems to reduce as you go down the group. So with that being said, let's move on to the next, what they call it, the next trend, or the next parameter that we'll talk about when you talk about trend. So the next thing is talk about ionization energy. Ionization energy. So this ionization energy is actually is the ability first for an electron to give off for an element or for an atom to give off an electron. You just see the atom say it has the ability to give up an electron. So the ability for an atom to give up an electron is what they call ionization energy. The ability for an atom to give up an electron is called ionization energy. So now this ionization energy now, it's as you go down the group, you know that they said this nuclear charge, the nuclear charge is the pulling force of atoms, is the pulling force. The nuclear charge is the pulling force on electron. So now, as you go down the group, we know that the ability to pull is reducing. So since we know that, since it is obvious now that the ability to pull electrons towards itself is reducing, it means as you go down the group, they will easily be able to give up electrons. It's easy to take up an electron from them because now you've covered them very well. Even if the electron that they have at the outermost shell, something can easily just come and collect it. It's like as if you have a shepherd that has plenty sheep. Then this shepherd has plenty sheep. If they tie this shepherd down, if they tie the shepherd with maybe one rope, tie with another rope, tie with another rope again, the person that they tie with one rope, before he can easily struggle his way out and save his sheep. But when you tie with several ropes, it will be easier for you to take off his sheep. So that's how the thing is. When the electrons they move down the group, their shell increases, and as their shell increases, they are covering their strength. So the more you cover their strength, the easier it is to take off an electron. So as you go down the group, the ionization energy reduces as you go down the group because of the same reason the shielding effect on the nucleus. As you cover the nucleus more, its ability to naturally, it's supposed to pull the electrons towards itself. But now, as you're covering it more and more, there's not that ability. So it will be easier for them to take any electron away from it. So as you move down each group, the ionization energy reduces as you move down each group. So and the reason for that is the same shielding effect. So while as you move across a period, as you move across a period now, the ionization energy becomes higher, because I said ionization energy is the energy that is required to pull up something. So someone that now you know that he is gymming. People that are the beginning of the period, they are slim. At the end, they are muscular, as I was saying. Even let's use the money aspect. I think that one will be more explanatory. The ones at the extreme, they have more money. If you carry case to want to rob them, maybe you carry a court case to want to win them in a court case, to carry their property. People that have money will be able to defend their property more. So before you can be able to defend someone that has money, you need to use much force, much energy to be able to steal his property. So that's how it is. We know that elements that are in the periodic table across a period, the ones that they go down towards the end of the period, they become stronger. So because they become stronger, to take anything away from them, you will need more energy. So that means the ionization energy, that is the energy to take off something from them, is going to be increasing as you move down the group. So I don't know whether it's clear. Are you guys following me?
Yeah, it's clear. Yes, I hear you.
Yes, sir. Yes, sir.
Okay. Okay, so that's how ionization energy is. You need to first know what ionization energy is. Then now, we already have tried establishing, from these different examples, we already started establishing that elements down across the period, as you go from left to right, the ones at the right, they have strength to pull electrons. So this is one thing that we know about them. The one at the beginning, they have weak strength to pull electron. So we already know that. So now, if you're not trying to look for energy to take off electron, those ones would have more energy. You will need more energy to take off anything for them because they are stronger. But as you go down the group now, elements at the top of the group, they have small covering, so they still have strength. They still have more of their hands that are free. As you keep on going down, they shield them more. So their strength, the ones at the top are stronger than the ones at the bottom to pull electrons. So as you go down, it's easier to take something from any of them compared to the ones that are up. So that's just the whole idea of this whole thing. Once you can be able to understand the nuclear strength across the period, and also the nuclear strength down the group, once you can be able to understand this thing, you can be able to tell these trends offhand. You can be able to tell it offhand because you just need to know what they're asking you for. Ionization energy is talking about the energy to take off an electron. So which people will be more stronger? Is it as you go down the group? Will the strength be increasing as you go down the group? Will the strength be reducing as you go back? Just that idea will help you to be able to understand these stuff better. So as you go down the group, the ionization energy reduces. While as you go across a period, the ionization energy increases. And I told you the reason why, because of the increasing nuclear charge. And the reason for the down the group only is because of the shielding is increasing. So let's move to the next slide. We are behind time. I think we are almost done with this. So the next one is electron affinity. Electron affinity. So electron affinity is the energy change when an atom gains an electron. So electron affinity is the energy change when an atom gains an electron. So from what we have, we said it becomes the electron affinity becomes more negative across a period. So first, you need to understand what electron affinity is. So it is the energy change, that is the strength change. So now we know that more energy will be consumed. More energy will be consumed to take something from when you go across the period. More energy will be consumed at the end. So because more energy will be consumed, you can say that the loss that you would experience, you'll be having more negative in your account balance if you want to challenge an old man, a rich man. If you want to challenge a rich man, you have to spend more money. That means you're having more negative. So this electron affinity, it is the measure of the change in your account balance. So because of you're trying to tackle a rich man, you need to spend more money. So there will be more negative on your account. So the change will be more negative. That is the affinity. You will need to experience the change, the difference between the initial money in your account balance when you try to go and fight a rich man and the final money in your account balance when the fight is over. it will be surely big, and it will be towards the negative side because you will lose money when you're trying to fight a big man. So that's what I said. Across the period, the electron affinity, which is the loss of money, it will be more negative. So, and to be less negative as you go down the group because of the same idea that I've been explaining so far, the same reasons are the same reasons. So now, if you want to down the group, we have poor men. So if you want to challenge a poor man, you don't need to spend more money. You will not have many losses to challenge a poor man. And we know that down the group, as you go down the group, you are going towards poor people's domain. So you spend less money to fight a poor man than it will take you when you are going across the period. Because going across the period, you're moving from poor to rich, going across the period. But going down the group, you're moving from rich to poor. So it will be preferable. The energy, the money you spend to challenge the poor people is more. So that's the affinity, the quantity of change in the initial point and the final point is what is the electron affinity. The change in energy is what they call electron affinity. I don't know whether it's clear. Does anybody have any question? If you have any question, just ask me. So before we move on. Hello? Hello?
Yes, we can hear you, sir. I can hear you, sir.
Okay. So that's for electron affinity. And that's just the trend is as you move down the group, the electron affinity is smaller, like it is less negative. Like the debit on the account is less. But as you go across the period, the debit is going to be more. I don't know, that analogy could be able to make you remember it easily. It's become more because more energy is spent. Since more energy is spent, it means that there's going to be more negative debits. So that's just the idea behind that. So let's move on to the next slide. Isoelectronic species. So when you hear the word iso, most of the time it means similar electronic species. That is species that have similar electronic charge. So that's just the simple definition of isoelectronic species. Isoelectronic species, they are species that have same number of electrons but different nuclear charges. Same number of electrons but different nuclear charges. So we already know what nuclear charges are. Nuclear charges are the charges at the center of the atom, the strength of the core of the atom. So isoelectronic species are species that have the same number of electrons, but different nuclear charge. So now, these species now we see here, these examples that I see here, we have oxygen -2. So this oxygen now, it has accepted 2 electrons. When we get to oxidation and reduction, we will know what it is. But this oxygen, it has 10 electrons. Fluorine has 10 electrons. Neon has 10 electrons. Sodium plus has 10 electrons. Magnesium 2 plus has 10 electrons. So all of them, they have the same number of electrons. But now their nuclear charges are different because in the nucleus of oxygen, we have 8 protons. Fluorine, we have 9 protons. Neon, we have 10 protons. Sodium, we have 11 protons. Magnesium, we have 12 protons. So the nuclear charges are not the same, but the number of electrons at the outermost shell or the outermost shell at the current time is the same. So that's isoelectronic species that they are species that have the same number of electrons in the outermost shell, but different nuclear charges. So ionic size decreases with increasing nuclear charge. So this is what we have been speaking so far. That as the nuclear charges increases, the size would always shrink. As nuclear charge increases, the size will shrink. So the same thing applies with isoelectronic species. Species that have more nuclear charge would have smaller size. If you have like this isoelectronic species now, we have this electronic species now, this isoelectronic species here. We know that this one has nuclear charge of 8, 9, 10, 11, 12. Their nuclear charge is different. So now, because the nuclear charge is different, you can tell automatically that this one has a stronger nucleus. So because of that, this one size will be smaller than this one, smaller than this one, smaller than this one, smaller than this one. So that's just the idea. The nuclear charge, the stronger the nuclear charge, the smaller the size of electrons. So that's the idea of all this stuff. So I think that should be the end of this lesson. So in summary, we talked about atomic size, and I said it decreases across the period and increases down the group. we talked about electronegativity, and we said it increases across the period and decreases down the group. The same thing we talked about ionization energy and electron affinity. I don't know, does anybody have any question before we round up?
You say the stronger the nuclear size, the what?
The stronger the
So,
nuclear charge, the
yes, sir.
stronger the nuclear charge, the smaller the size. The stronger the
Okay,
nuclear
sir.
charge,
Thank you.
the smaller the size. Yeah, so that's for that. So does anybody have any other question? Maybe 2 more questions before we just wrap up. Like, so I'll just end the class now because we are behind time, I believe so. Yeah, we just overshot time by 3 minutes. So any other question? Okay, I think that will be the end of
Hello?
today's lesson.
I
Okay,
have
someone has a
question.
question. Okay, I'm listening.
The question my fellow student asked now. You said that the stronger the nuclear charge, what will happen?
Yes, the smaller the size.
Okay. Is it the same thing, the nuclear charge being stronger? Is it the same thing as a nuclear charge increasing?
Yes, it's the same thing.
All right.
Yeah. So that will be all for today's class. And thank you all for attending. And I will see you guys